Welcome to Signal Processing Laboratory. So in this video we are going to see about the second experiment, that is representation of 2D image signal as the linear combination of PCA. So PCA is nothing but the principal component analysis. So the Eigen decomposition of symmetric positive semi-definitive matrix, so it will yields an orthogonal basis for eigenvectors. So each of which has a non-negative eigenvalue. So the orthogonal decomposition of this PSD matrix is used in multivariate analysis, where the sample covariance matrix is called as this positive semi-definitive matrix. So this orthogonal decomposition is called as principal component analysis in statistics. So we are going to see about this PCA here. So the PCA studies linear relation among variables. So the PCA is performed when the covariance matrix or the correlation matrix. So for the covariance or correlation matrix, the eigenvectors corresponding to the principal components and then eigenvalues to the variance is explained by the principal component. So next is the eigenphase generation. So here a set of eigenphases can be generated by performing a mathematical process called principal component analysis on a large set of images depicting different human faces. So here we are going to use a database of human faces. So on that the images, so a set of eigenfaces can be generated by performing some mathematical operations called principal component analysis. So eigenfaces can be considered as a set of standardized face ingredients derived from the statistical analysis of many pictures of faces. So any human face can be considered to be a combination of these standard faces. For example, one face might be composed of an average face plus 10% from eigenface values, 55% from eigenface 2 values, even -3 from percentage from eigenface 3. So it does not make any eigenfaces combined together to achieve a fair approximation of most faces. So also, because a person's face is not recorded by digital photograph but instead a list of values here, so much less space is taken for each person's face. So the eigenfaces that are created appear as light and dark areas that are arranged in specific pattern. So this pattern is how different features of faces are singled out to be evaluated and scored. So let's see the practical implementation. So we have to prepare to create an eigenfaces. We have to prepare a training set of face images. Picture constituting the training set should have been taken under the same lighting conditions and must be normalized to have eyes and mouths aligned across all images. Then each image is treated as one vector simply by concatenating the rows of pixels in original image, resulting in single row with R and C elements. For this implementation, it is assumed that all images of the training set are stored in a single matrix T, where each row of matrix is an image. So all the images are stored in a single matrix. So each row of the matrix represents a single image. So for example, if you have 400 images, so then all the 400 images are stored in a single matrix where each row, so the matrix will have 400 rows and each row will represent the single image. Then we have to subtract the mean. Average image A has to be calculated and subtracted from the original image T. Then we have to calculate the eigenvectors and eigenvalues of covariance matrix. Then choose the principal components. So when we follow the above steps, we can generate the eigenfaces. So these eigenfaces can now be used to represent both existing and new faces. So we can project a new image and the eigenface, thereby record how the new face differs from the mean face. So the eigenfaces associated with represent how much the images in the training set vary from the mean image in that direction. So we lose information by projecting the image on a subset of eigenvectors, but we minimize this loss by keeping these eigenfaces with the largest eigenvalues. So in practical application, most faces typically we identified using a projection between 100 and 150 eigenfaces. So the most of 10,000 eigenvectors can be discarded. So here is the program. So we can execute it in MATLAB. So here we are having 40 subjects. So for each subject we are having 10 images. So in order to load that image, we are using these two loops. So there are 40% image we are having, and this for each person there will be 10 images taken in the same lighting conditions. So we are reading these values and finding the covariance matrix and finding the eigenfaces here. Then we are finding the error images. So let's run the program. So these are the compressed images we are getting. So this is the original image. This is the compressed image. So this is the 25 eigen basis images for that 25 images. Then we are getting the sum square error between original images and the compressed images. So we will see the next experiment in the next video. Thank you.